Okay, hello everybody. Let's take a minute to talk about factors of safety. In theory, we could design all of our material to their either yield strength or their ultimate strength, right? So if we were designing something and we had something that was, say, some material that was made out of A36 steel. Well, we know that A36 steel has a yield stress, a sigma y of 36 ksi, and maybe we're designing something for out of A36 steel, and we don't want to load it all the way up to the 36 ksi, just because there may be some other unforeseen circumstances or some uncertainties. These could include something like what the material, the different materials may have different, air pockets or deficiencies in when the material was being developed into whatever it is that we're analyzing. Also, different loading situations where you have, people are the worst. If you tell them that they can only load something up to a certain weight, they're gonna definitely push that to the limit and probably estimate and go over. Any inaccuracies during the erection process, or any of that kind of stuff. So we add this safety factor in there to try and compensate for those uncertainties. So there's two ways that we're going to do it in this class. The first way is that we can define a factor of safety as being the failure stress of our material divided by the allowable stress. As a second method, what we can say is a factor of safety is equal to the force that would cause failure in our design. And by failure, it could either mean at the yield point or ultimate failure, divided by allowable. Allowable is what we're actually going to work with, right? So with these two methods, the first one, what we're really doing is we're, in essence, pretending the material is less strong than it actually is. And with that, we're going to design for a lower overall stress. So if I had an A36 steel, it's basically saying, oh, well, it can handle 36 ksi, but we're going to pretend like it only can handle 18 ksi. Now, the way that I recommend you do this is you have your design stress. So, for instance, like I said, if it's 36 ksi, we're going to reduce it by this safety factor. So, whatever type of stress we're dealing with, this would be our A36 if we're dealing, or 36 ksi if we're dealing with A36 steel. Then we're going to divide by safety factor. So, if we wanted a safety factor of 2, then we would use 18 ksi instead of 36 ksi, or whatever material we are using. So that's one method to use. The method that I'm going to use most often, and I think it makes a little more sense, is if we were to look at our design forces instead and say, all right, if we're designing to hold, 100 kips or something like that, what I'm going to do is in the very beginning, I'm going to take whatever safety factor I'm designing with, I'm going to multiply that times whatever forces are given in the problem. So if I'm trying to design for 100 pounds or 100 kips and I need a safety factor of 2, I'm just going to multiply the 100 times 2 and design it as if it's 200 kips. In essence, saying that we'll compensate for these uncertainties by making sure our structure will handle twice the amount of loads. And you can probably see where this why one is multiplying and the other one is dividing. If we just have our, last time we said sigma is equal to P over A. If I wanted this safety factor, I'm going to put it in the 2 somewhere. It's either dividing this by 2 or I can multiply both sides by 2. And, you can kind of see how that would fit. So let's go ahead and look at a brief example of using safety factor. What we're going to be looking at is we're going to try and design a cable diameter to hold a 100 kilogram chandelier using a safety factor of 3, and we're going to make it out of steel. All right, so if I had to draw our situation, what we're saying is hanging from the ceiling, we'll have some kind of cable. It's my handy dandy chandelier, which has a mass of 100 kilograms. or as a free body diagram, what we're really looking at is our little support here, which converting our kilograms into a force, multiplying times 9.81, I end up with a 981 Newton force in tension for this cable that's holding up our chandelier. So looking at both methods, the first method is let's design for a lower stress, and I can see that I have a yield stress of 200 megapascals. I can look that up in a table. In this case, it's given in the problem for steel. So we're going to design, instead of 200, we're going to design for 66.67 megapascals. Going to our fundamental equation, we learned last time which sigma was P over A. Rearranging this to solve for the cross-sectional area needed in order to support this load, P over sigma, I have 981 newtons divided by this new load, or this new stress with the safety factor included, 66.67 megapascals. And you can check your units, but like we said last time, if you're working in newtons and megapascals, you end up with a unit of millimeters. This one's area, so it's 14.7 millimeters squared. And then the next step would be, well, we know the area of a circle is equal to pi over 4d squared. So from that, I know my diameter must be equal to the square root of 4 times area over pi. Plugging in that area, I end up with 4.33 millimeters. Now, one thing you cannot do, and mathematically you could probably see this pretty quick, is you cannot solve the whole problem like you would have without a safety factor and say, well, I have a 4.33 millimeter diameter cable, I want a safety factor of 3, I'm just going to multiply that 4.33 times 3, or whatever answer you would have got. It doesn't mathematically quite work like that. The alternative method that I'll use in this class more times than not, though, is I will just start from the very beginning and take all of my loads and just multiply it by my safety factor, or 2,943 newtons. Doing this and going through the same problem, you would see that the area needed is this 2943 over our 200 megapascals, ends up with the exact same 14.7 millimeters squared that we got up above. And of course I could do the same next step and get the same 4.33 millimeter diameter. So like I said, this is the second method is what I tend to do. The reason I like that is because I do it at the very beginning of a problem. I just take my safety factor, I put it right into the loading, because that's always given, usually it's given, and go from there. So I hope that was helpful, and I look forward to talking to you soon. Thanks.